Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at the lab exercise relative dating. So relative dating is a process that all geologists have to employ when they're doing work involving stratified rock. So when your sequence of rocks is split into distinct layers. Now it's the earliest form of dating that was produced by geologists, because you need to remember that radiometric dating using radioactive isotopes and their decay wasn't really a viable prospect until the 1940s, and in reality it wasn't really you couldn't really do it easily until the 1960s. So before that, the only real way to date a rock was to do it in a relative fashion, and this means that you are simply putting the rocks into a chronologic sequence by using the relationships between them. And by doing this, geologists came up with a sequence of principles, which are called the principles of relative dating, and they allow you to put the rocks into that chronologic sequence. You also need to take into account the formation of unconformities as well when you are dealing with relative dating. So the history of relative dating essentially goes all the way back to the early geologists. So we're talking all the way back in the 18th century. So what we have is a situation where we have geologists who were going out into areas and they were looking at the rocks in that area. And so what they would do is they would put together things which are referred to as systems. So a system is simply a package of rocks, and it's an arbitrary package of rocks. So that the geologist has simply said, right, my system is going to start here and my system is going to end here. And typically where they start or finish their system will have some kind of distinctive feature. So for instance, maybe the system will start or end on a very distinctive rock type, or normally the system will start or end on the first appearance or last appearance of a very distinctive fossil. So what happened was you had lots of geologists doing this, and so they, each geologist put together their own individual systems. And then once, the other geologists found out about these systems, they began to work out what the exact chronologic order was for these systems relative to one another. And so what you ended up with is, once you put all of these systems into their correct chronologic order, you essentially had the first geologic timescale, with the Cambrian system going all the way through to the Cretaceous system. Now, obviously, you've probably just thought to yourself, hold on a minute, that doesn't include the Cenozoic, and yes, you're very right about that. The Cenozoic was treated slightly differently and dealt with in greater detail later. So what we're primarily talking about here are the periods of the Paleozoic and the Mesozoic. So the systems are essentially the basis for the periods of the geologic timescale. So Cambrian, Ordovician, Silurian, Devonian, Carboniferous, or Mississippian, Pennsylvanian in North America, Permian, Triassic, Jurassic, Cretaceous. And we also know that, we also split these systems into smaller units and larger units, and so these smaller and larger units are also the basis for the eras of the geologic timescale and the epochs and the ages. And so all of this combined together essentially led us to the formation of the earliest geologic timescale. So what you had was a sequence of rocks which have been put into a chronologic order. But the other more useful thing was that as part of this sequence of rocks, you actually had the fossils put in a chronologic order. So what you could do is you could go to another location and you could say, right, I have found fossil A. What period does fossil A appear in? So then you go look at the publications, and you find that fossil A appears in the Silurian. So therefore you know your rock is from the Silurian. But then you can go into it in even greater detail. You can say, right, well, which epoch or age did this particular fossil appear in? So you can really narrow down the age of your rock. Now, the thing is that the age you're giving, so Silurian, does not have numerical values associated with it. Those come later once radiometric dating becomes common. All you can really say is that, yes, this rock formed during the Silurian, and that's about it. But that's about as good as it gets with relative dating, because unless you have a process that allows you to get a set numerical value, all you can really do is put your rock and the fossil within it, within the chronologic sequence. So by studying sequences of rocks, geologists came up with 7 principles of relative dating, which hopefully you've watched the relative dating video, so you know what these 7 are, but let's go through them. Superposition, original horizontality, lateral continuity, principles of cross-cutting relations, principle of inclusions, baked and contact zones, and the principle of fossil or faunal succession. And so for each one, there is a definition. So for superposition, it simply says if you have a sequence of rocks, the oldest rock will be at the bottom and the youngest rock will be at the top. And this works in the majority of cases. There are some situations where the sequence has actually been overturned, so the oldest rock is actually at the top and the youngest rock is at the bottom, but those situations tend to be less common. So original horizontality simply says that when a layer of sediment is deposited, it will initially form a horizontal layer. So if you walk up to a sequence of rocks and you see they are tilted, that tells you that that tilting must have occurred after the layer of rock formed. So if your layer of rock is folded or warped in some way, that process must have occurred after the layer of rock formed. So the next principle is the principle of lateral continuity, and that simply says your layer will extend in all directions laterally until either it runs out of material to form the layer, or that layer hits some kind of vertical surface and can't go any further. Then there's the principle of cross-cutting relations. And so the principle of cross-cutting relations simply says that if you have a fault or a dike cutting a sequence of rocks, the fault or dike must be younger than the sequence of rocks that they are cutting, or it is cutting. So if you have, a sequence of rocks with layer A, layer B, layer C, and then they're cut by fault D must be younger than layers A, B, and C. So then we have the principle of inclusions. That simply says that if you have a rock that contains inclusions of another rock, that can be in the form of clasts if it's a sedimentary rock, or in the form of xenoliths if it's an igneous rock, then these clasts or xenoliths must be older than the rock in which they are contained. Then we have the principle of baked zones or contact zones. And that simply says that when you have magma intruding a sequence of rocks, the heat from that magma will cause the rocks along the edge of the body of magma to become baked. It will heat them. And this will lead to contact metamorphism, and it will lead to the rocks changing. And so this process of baking the rocks, heating the rocks due to the magma entering, tells you quite clearly that the magma must have entered the sequence after the layers of rock had formed. Okay, because if you have a situation where for instance, the granite was exposed and then sediment was deposited over the top of it, well, you wouldn't get a baked contact because the granite was already solidified when the layers of sediment were deposited. However, if you have a situation where the felsic magma intruded a sequence of sedimentary rocks, you would see the baked contact, and that would tell you that the intrusion entered them after the layers of rock had formed. And then the final principle is the principle of faunal succession or fossil succession. And that simply says that fossils occur in a known and predictable order. So we know where each fossil sits in the geologic timescale. So when we see that fossil, we can say, right, this rock is from the Cambrian, this rock is from the Cretaceous, this rock is from the Permian. And it's a relatively straightforward system, and the principle of faunal succession is based on those early works that started to put fossils into a chronologic order. And of course, never forget that fossils are the basis for the boundaries in the geologic timescale. It will be the first or last appearance of a fossil, or certain or more than one fossil will allow that boundary to be located. Now, another thing that we need to think about, and was also observed by these early geologists, were unconformities. So an unconformity simply represents a portion of the rock record which is missing. And so when you look at a sequence of rocks, they may look as if they form a nice continuous sequence. However, if you look at the fossils in them, for instance, you might notice that you have a sequence of rocks. You have the Cambrian, you have the Ordovician, you have the Silurian, and then all of a sudden you jump to the Permian in the next layer of rock. And then you think to yourself, well, hold on a minute. We seem to be missing the Carboniferous. Where's it gone? And so that will be an unconformity. You are missing a portion of the rock record. It's gone, been destroyed. And the most common way that that occurs is through erosion. And so in most cases, what happens is the sequence of rocks is pushed above sea level to a point where it is exposed and can therefore be weathered. And the process of weathering will destroy rock. And so as that weathering is ongoing, it's obviously going to destroy the rock, and then eventually the rock finds itself in an environment where new sediment is deposited over the top, and therefore the sedimentary layers start to build up again. And this will result in a situation where you have a sequence of rocks where once you date them, you realize, hold on a minute, there's a portion of the rock record which is no longer there because it was eroded away. So in terms of the different types of unconformity, there's actually 4 different types. So the first type is the disconformity. And in a disconformity, you have a situation where the layers of rock above and below the disconformity are horizontal. However, the unconformity itself undulates, it wiggles up and down, it's uneven. Then we have an angular unconformity. And an angular unconformity is essentially a surface where you have tilted rocks below the unconformity and horizontal rocks above the unconformity. And actually, if I just drop down to figure 4.2, you can actually see the original example of an angular unconformity. So this is Sickaire Point in Scotland, and the unconformity itself is marked out here by the dashed white line. So you can see below the dashed white line, you have a sequence of vertical Silurian greywackies, and you can see the layering right here. It's top to bottom. Now above them, you can see you have this unit where the orientation of the beds is obviously very different. You can also see they have this kind of distinctive red-brown color to them. So this is a mixture of Devonian conglomerates and sandstones. These are desert deposits. And you can see that compared to these vertical Silurian greywackies, you can see that they are horizontal. Now, I'm going to be honest, the entire sequence has been tilted slightly later, which is why these beds here aren't perfectly horizontal, but I think it gives you the idea of what an angular unconformity is. So an angular unconformity, you have tilted rocks below the unconformity and horizontal rocks above the unconformity. So then we have a nonconformity. This is essentially the contact between any sedimentary rock and an igneous or metamorphic rock. So wherever you have sedimentary rock in contact with an igneous rock, that is a nonconformity. Wherever you have sedimentary rock in contact with a metamorphic rock, that is a nonconformity. The final type of unconformity is a paraconformity, and these are often the most difficult ones to actually find. So what you'll have is you have a situation where the layers of rock above the unconformity are horizontal. The layers of rock below the unconformity are horizontal. The unconformity surface itself is also horizontal. So you can't actually see it's there. And you don't realize a paraconformity is actually there until you date the rocks above and below the unconformity, at which point you go, oh, there's some rock missing here, there's a portion of the geologic record which isn't present, I therefore have an unconformity in this location. So all of this information can be used to produce a relative sequence of rocks for an area. Okay, now once again, I've obviously just given you a very quick verbal rundown of each of the principles and the different types of unconformity. Please, if you want to see images of what I am describing, go and look at the relative dating lecture. All right, it has images and it has much more in-depth explanations about these topics. So before going on to part 1, please take the time to look over that lecture. Okay, So for part one, you are going to be looking at several different diagrams, and your aim is to put the rocks within these diagrams into a chronologic order. All right. So as you can see, here is figure 4.3. You can see it's a diagram that consists of 5 layers of rocks. We have A, B, C, D, and E. Please notice that the letters are mixed up a little bit. They're jumbled up. That's just to make your life a little bit harder. So in terms of the sequence, so for question 1, you're going to look at it and you're going to think to yourself, right, which principles are going to apply to this? Well, you have a sequence of horizontally bedded rocks here, so A, C, B, and E. So you're probably going to think to yourself, right, the principle of superposition is probably going to be useful in this instance. That's going to give me some information. Another principle that you can employ is you'll notice that D clearly appears to be an igneous rock, and it actually says so in the text of the question as well, just to make sure that that point is made clear to you. So D is an igneous rock. And so when you look at D, you're going to think to yourself, right, well, one of the principles here tells me something about the age of intruding rocks relative to the rocks that they are intruding. So this intrusive rock here, it's going to give us some information about its relative age compared to the 4 layers of rock here. And then finally, you will also notice that rock D, our igneous rock, contains pieces of the other 4 layers here. There is also a principle that focuses on that, and that can also be used to help you put the rocks in a chronologic sequence. So what you're doing is you're simply employing the 7 principles of relative dating, and you are using them to put these rocks into a chronologic order. Now for question 2, it's going to ask you which 2 principles of relative dating can be used to show that the intrusion, which is D, our igneous rock, is younger than beds A, B, C, and E. All right, so you're simply going to have to work out, right, which of the 7 principles here did I use that told me that D was younger than the other 4 layers of rock. So for question 3, you can see we have another diagram. This is figure 4.4. And once again, we have another igneous rock. In this case, it is A. Okay. You will also notice that there is a fault, D, and an unconformity, G. So we have lots of stuff going on in this diagram. So the first thing you'll notice is for C, B, and E, you can see that, well, we have these nice horizontally bedded rocks. So this means that the principle of superposition is probably going to be helpful here. We also obviously have some kind of igneous dike, which is A, and we have a fault, which is D. So the principle of cross-cutting relationships may be helpful in this instance. We also have the unconformity G, which you'll actually notice cuts fault D. Okay, so you'll notice that fault D stops, it terminates at the unconformity. That's going to be important for you to put D and G in the correct sequence. And then finally, we have F over the top of everything. So when you look at figure 4.4, please take a minute to work out what type of fault is D. Okay. If you are uncertain, there's a few things you can do. You can go back and look at your physical geology notes. You can email me, or if push really comes to shove, there's always Google. So for question 5, what you're going to do is you're going to put the rocks in figure 4.5 into a chronologic order. So here is figure 4.5. As you can see, we are getting steadily more and more complicated in the diagrams that you're having to deal with. So straight away, you can see that the sequence consists of a lot of horizontally bedded rocks. So the principle of superposition is going to be extremely helpful to you here. You can also see that you have 2 faults, G and D, and you have an unconformity, I. So the principle of cross-cutting relationships is also going to come into play. So one of the things that I do want you to notice when you look at figure 4.5 is that which rocks are cut by the faults. Okay, so if you have a layer of rock, let's say C, you'll notice it's cut by the fault here, it's truncated by it, and it's also cut by the fault on this side as well. All right. Now, even if you don't have the same layer of rock on each side of the fault, so for instance, F, okay, if we look at F, we can quite clearly see that it is cut by the fault right here. However, we can't see F on the other side of the fault. Even though the layer of rock F on this side of the fault isn't visible in the picture, we can see that F has clearly been cut by the fault. So you can then employ the principle of cross-cutting relationships, and you can say, right, which one was there first, F or G? So once you've done that for figure 4.5, you can then come to question 6. So in figure 4.5, what type of faults are D and G? All right, so that's just essentially, that's very similar to question 4 here. Once again, if you have difficulty identifying the type of fault, go back to your physical geology notes. If it's still not working out for you, email me. And as a last ditch, please go to Google. Although please try and get in contact with me first. All right. So question 7 is dealing with figure 4.6. And if we drop down here is figure 4.6. And you can quite clearly see that there is a lot of stuff going on here. This is a very interesting diagram. So first of all, you can see that we have several layers of rock here. So we've got D, F, M, N, and C. And you can see that they're all orientated parallel to each other, but they've clearly been tilted. So even though they've been tilted, the principle of superposition is definitely going to be helpful to you here. You can also see that we have some unconformities marked on. Now, D is a metamorphic rock. Okay, I'm going to repeat that again. D is a metamorphic rock. F is a sedimentary rock. So that means there's going to be an unconformity there. We also have an intrusion, we got a dike here spreading out to a sill here. And that's labeled as A. And you can see that it's quite clearly cutting across some layers of rock. But you can also see that A has been truncated, been cut by this unconformity here, which is G. So that's also going to be important in putting things into the correct order. You can then see that B has cut all of these layers of rock here, and it has also cut the the unconformity right here. So notice the unconformity, which is labeled as G, stops, it disappears, it's being cut by intrusion B. That's going to be another important piece of information. Now, once you get above this sequence, we have unconformity I, and then you can see we have a sequence of nice horizontally bedded rocks. So obviously, principle of superposition is going to be useful again there. And then you can see that nearly the entire sequence is then cut by H, which is obviously some kind of igneous rock. And so, use the principle of cross-cutting relationships to put that into its correct location in the sequence. Okay, so once you've put the rocks in figure 4.6 in chronological order, you need to answer this question about the different types of unconformity. So unconformity I, all right, it actually is two different types of unconformity. So when you look at unconformity I, here it is, coming across here right there. But along the length of it, it's mostly one type of unconformity, and then it actually changes into a different type of unconformity. And so question 8, is simply asking you which two types of unconformity make up unconformity I. So for question 9, you are going to go to figure 4.7. Here it is. Yep. Once again, we're getting even more complicated. And you can quite clearly see that these lower layers of rock have most definitely been folded, haven't they? It's quite obvious. You can also see that they've been folded and they've obviously been cut by whatever this igneous rock is here, which is H. All right. Now, the one thing I would point out to you is you're probably thinking to yourself, well, hold on a minute. How do I know what the relationship is between H and M and Q? Because when you look at the diagram, you'll notice that H clearly cuts P, J, A, F, R, and B, but it does not cut M and Q. So you have to think to yourself, well, are there any other pieces of evidence that I can use here that's going to give me some information about the relative age of M and Q relative to H? And The one thing I would ask you to notice is that P, J, A, F, R, B, M, and Q are quite clearly folded. Is H, yes or no? Is it folded? So that's going to help you put H into context of these other layers of rock. So obviously the principle of original horizontality is going to be important here. Now, once you get above this, you're obviously going to end up at unconformity E, and then you have a sequence of nice horizontally bedded rocks, so principle of superposition. Then you have another unconformity, L, more horizontally bedded rocks, principle of superposition again. You can then notice that you then have N coming through. N is clearly an igneous rock again, because it's feeding some kind of volcano at the surface. Okay, and you can see that N has taken a path along another feature. So notice how C, G, and K are clearly offset. So C has clearly dropped down, same with G, same with K. So there's obviously another feature here that's being hidden by the dike that leads to the volcano at the surface. So one of the questions are going to ask you to try and work out what that feature is. So here we go. So once you've put the rocks into a chronologic order, which is question 9, you'll then move on to question 10. And so that says in figure 4.7, what specific geologic structure is concealed by rock N? Okay, so when I say specific, I mean specific. Don't just say, oh, it's a fault or it's a fold. If it's a fold, for instance, is it an anticline or a syncline? If it's a fault, is it normal? Is it reverse? Is it strike slip? I want you to be accurate about what feature is being hidden by the igneous rock N. Finally, in figure 4.7, what geologic structure is formed by rocks A, B, F, J, M, P, Q, and R? And you can see you have 3 options: lead, intrusion, syncline, anticline. Please select the correct option. If you are uncertain about what these terms mean, please once again refer back to your physical geology notes. If you still can't find the information you need, please email me, and as a last resort, Google. Okay, so I think this is time we stop this video, so please get up, take a break, have a walk around, get a drink of water, and then return for part 2.